Greetings to our viewers.
Yes.
What's going on? I do science. Crina is interested in science and wine. I am interested in wine. We are drinking wine and discussing science.
Cheers. Nice. So, what we're going to discuss today?
Today, I want to tell you excellent men topic. You know, in the former times, everything was controlled by men.
Oh, really?
Yeah.
Unexpected.
And what did men make? Wonders of the world. They're huge. You know,
I see where it's going.
The Hadron Collider, you know, it's large. Basically, men have done everything huge, large, and so on. And today, I want to say about the best experience in enlarging.
Oh God, men being men, you know, as usual. It's something like typical. We're gonna speak about 15 centimeters. That's like unbelievable.
And today we are speaking about Rydberg atoms, which are unimaginably large. If you want to enlarge, expand something, you are quite limited. Even if you have a balloon, you can blow it and it will be like 10 times bigger, 15 times bigger.
Yeah.
Maximum, I know, 50, not even 100. But there is a thing you can make bigger by 10,000 times, roughly. 10,000 times in one dimension. And in
the joke is continuing, or like you're being serious?
So
oh God.
10,000 times. And you know what it is?
You're gonna tell me now.
It's an atom.
Oh.
You can make atom 10,000 times bigger and figure out how huge a change in the volume. In the volume.
It's like
I
crazy.
Right
here, yeah. I'm continuing my task, you know.
It's quite tough to figure out the sizes of the atom because we never experience in our daily life. What, let's say you have a residential building and you have your hair.
Yeah, one piece of hair.
And the difference is exactly 10,000 times roughly.
Whoa.
Is exactly roughly 10,000 times.
Oh, okay.
And if you continue as a trend, the atom is 10,000 times smaller than the hair.
Damn. Okay.
It's
so
that smaller.
From that small, teeny tiny size, you're trying to...
hard to imagine.
Surprisingly. Well, actually, with this example, it's easier. Yeah, thank you. Nice. And you mean but that this atom can be made bigger, right? How big it can be?
Up to roughly the size of the hair.
Oh, really?
And probably even bigger. We do not know the exact limits. Different people claim different, but to the size of the hair, we basically trust.
Okay, interesting. And how do we make it?
It's a trick.
It's a secret.
It's a secret, but...
The video's it's over.
But I will tell you, and it will be no secret anymore.
Okay.
The size of the atom is limited. It's usually defined by its Bohr radius. And for the hydrogen atom, please show the formula.
Over here.
And I just shown you in advance. It consists totally of the constant, of the Wolf's constant. You cannot change them. But there are two tricks. How to avoid the problem itself, I will tell you now, and how to change Wolf's constant will be in the second part of the video.
Yeah, so stay tuned.
That's the Bohr radius, and it's for the ground state of the atom. But you know, you can't change from the ground state to the excited state. You kind of kick it. Usually you shine with the photon. It absorbs photon, and it changes from one state to another. There is a set of states. Please show it.
Over here again?
Yeah. Wait, there is one thing I didn't pronounce that clearly. How size of the atom or its radius depends on the principal quantum number. Radius rises as a square of the principal quantum number, so for the second state, its radius is already 4 times bigger. For the state number 10, its size already exceeds 10 nanometers, so it's bigger than the modern semiconductor transistor. And for the state number 100, it's already 10,000 times bigger. And just think what happens with the state number 400. I would expect already something of the size of an apple. At the beginning, they are like separated by high energy, but the distance reducing, and they are saturating at some limit.
Yeah.
At this very place, it's already hard to, like, if you jump a bit higher, you are in danger, it can just flow away. But you can easily vary it within this size, and from the level of, 1 to the level of 100, you can more or less move it.
Oh, nice. How to do it?
Yeah. To do it, you have to since the difference in energy at the lower levels corresponds to visible light, you just shine the light. Then but the problem, you cannot match precisely to the certain levels of the high, because they getting that dense, you will not just shine directly. First, you do a few jumps with light, and then this spacing is that tiny, you can apply microwave, and then you shine with microwave and go further and further. This way, you can reach levels of, as far as I know, 50, 60, 70.
And what does it give us? Like enlarging it?
Enlarging it looks like a purpose, but it's not a purpose, it's just, let's say, side effect.
Yeah, the purpose was actually to make this atom bigger.
The purpose was to reach this level, because at the higher initially, and it was a Nobel Prize for.
Oh, really?
Study.
Another one. Nice part.
Yeah.
And the names of the guys?
I don't remember.
Wait.
Probably you.
I'm gonna help you. I have a cheat sheet here. It's Serge, Haroche, yeah, and David Winterland. Winterland is easier to actually.
Winterland and the first one.
Yeah.
With all the respect.
Serge. Yeah. We have no. Actually, I don't know how to pronounce it. I will Google it.
So what was then? The huge atoms. Why did they do it? Because they wanted to manipulate with the states, and they shined some laser to reach this level, and then the higher states have higher lifetime, because it's like more. The electron is already far away from the nuclear, and it's tough to drop down. Therefore, it can live for, I don't know, microseconds even. I mean, in the scale of atomic business, microsecond is a very long time.
Yeah, so
because usually it's like nanoseconds, like.
Yeah, you're speaking about other topics, right? Before, when you're saying like that, actually, it can be this time and interval, like it's really small. You
want to keep it for longer possible time, because as longer you have it, as more manipulations you can do. For example, like quantum computing, you can apply many operations. While if it's rapid, you can apply, I don't know, 2, and you will not be succeeded.
Yeah, that's true. And you said about the advantages it gives, and that actually it was the Nobel Prize. Also, it's a nice thing. People can watch this video and then Google and get more information about that, which is, I think, it's wonderful. So please do that.
Basically, the description on the Nobel Prize committee is excellent. Always. There is easy one, there is a tough one.
Yeah, so you enlarge your vocabulary, your knowledge, you see? Keeping the track of that joke.
I told you, enlargement is a good business.
The next thing.
If we had a sponsor, I would ask some sex shop.
Tell me, please, about applications.
So the applications I told you, basically, they are 2. First of all, of these, you can make quantum thing. You can manipulate with the microwave. Because at the high state, you do it with microwave, and you control a quantum bit with quasi-microwave on. Excellent.
Oh, nice.
Secondary, you can use it as a sensor of electric field. People say, like, if electron and a core, they are separated by huge distance, it has a huge dipole, and huge dipole senses the electric field quite good. I am not that experienced in this very field. Probably if there is a specialist as my classmate, write in comment what are the applications. But I would say it's a bit fundamental. but it's up to 65th level.
Oh.
And with the 65th, you have a size like, I don't know, 4,000 times bigger than the usual, but I promised you 10,000.
Yeah.
And for this, you can go to the higher levels.
Yeah.
It's not that direct as you can imagine, because it was, I told you, like, with this n square for hydrogen atom, but not the hydrogen atom was enlarged, so blah, blah, blah.
And we cannot do this blah, blah, blah.
This blah 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 means the formula getting more complicated. I do not want to even show you that much because
Don't get scared.
Don't get people scared. But the idea at the level of 400 for the certain atom, I guess it's cesium or rubidium. I don't remember which exactly. Some heavy atom, not hydrogen. In size, it reaches 25 microns. While your hair is roughly 50.
Oh, okay. Interesting.
Crazy.
Yeah.
From such like sub-nanometer to 25 micron. And there is a work which says also about a level of 1,000, even bigger, probably like snowball, but they do not claim the size exactly, in contrast to the previous work where they say like, it's about 12 micron in diameter, in radius, so 25 in diameter.
Okay.
But with the work 1,000, I don't know. It's crazy.
What you can do with that as well. So it's like
just surprise.
Surprise, surprise!
Have you seen such huge atom? No.
Giving to your kid, like this information for. So which are the limits actually? How high we can get?
And the problem is that the spacing between levels getting smaller and smaller, and at some moment it's already that small you cannot really, like, the energy is too small compared to what? Small is not arbitrary. Compared to temperature. If the temperature, for example, is not that small, it will be already jumping between, and you do not like feel it as a quantum system. That's already like
something that is not as stable.
Like if
right?
you shake person, it's like
and not that useful as well, right?
Yeah, it's already. And the problem, let's say, not only between those levels, but it means you have like levels, and after some, it will just fly away, getting this temperature energy.
Oh.
So it will not be even stable.
Yeah. So we have this 50 where is the stability, like it's the most stable.
The 50, 70, they are quite stable. 400 is for like world's record. 1,000 probably also like, wow, guys, what I can do. But it has no...
Like, maybe there will be other researchers and there will be some things added and again to the formula, or?
I wanna the second part.
Yeah, so like I'm hinting about that. So we maybe go to the second part, and we discuss.
So there is a formula which defines the size. Yeah, and you can see here mass, which for electron is kind of unchangeable, and Planck constant, which and pi, or what can you change? But basically, if you work with the free electron, it has a certain mass. But if you put it into solid, into crystal, into silicon, it is already different. You work not with the mass, but with the effective mass. And the effective mass...
That's my house. When it's messy, it's effective. Sounds good. Yeah, so you're working with the effective mass. Yeah.
Which is roughly 20 times smaller.
Okay.
If it's 20 times smaller here,
it
means the value will be 20 times bigger. Then you have electrical permittivity. Crazy word. It basically reflects what's a surrounding. If the surrounding can be like polarized by the electric field. For vacuum cannot be polarized, but the crystal can be. So you basically, in crystal, can get this factor of 20 roughly. So in total, you can have the atom bigger like 400 times. That's already quite a lot.
Yeah, that's considerable. And
So the
And
question
what
how
did
to
you-
get
Yeah,
the question
this
is how to get atom in the solid.
How? How is to get the atom into solid?
For this, we will begin with the philosophical question: what is the atom itself?
So what's the atom itself?
Atom itself is just some positive or some heavy particle with one charge
Yeah.
and lighter particle with another charge.
Yeah. Plus, minus. Yeah.
So the lighter particle creates levels around the heavier one,
Mm-hmm.
and it's kind of this, the orbitals like from the chemistry classes.
Yeah.
And in our case, we have like proton and electron.
Yeah.
But in the solids, you can find electron and hole.
So,
so-
void. Yeah. Something that is not
Hole,
filled with something.
I believe people mostly know what is a hole. It's kind of
Mhm.
absence of electron, whatever. But it's real positively charged particle. And they establish the structure which exactly is an atom. And it is called exciton. Kind of, if the electron is placed into this hole, they annihilate quasi, giving you this
Okay.
piece of light.
Mm-hmm.
And if you shine this light back, it kicks electron from its position.
Outside of it, yeah.
You have a hole, you have electron, and that all is kind of excitation. So it's called exciton. It's quasi-particle. Fancy word, probably once we will speak about.
Oh, nice. Yeah. Is the whole study going around it? Oh my God. So we have.
I have published it.
Oh, really? So there's a video with that thing. Let's go back now with the. What's called it again? Help me.
Exciton.
Yeah, with the exciton.
So exciton is basically like an atom. It can be considered as an artificial atom because establishes the structure of the atom.
Yeah.
So you can again enlarge this atom, given it higher principal quantum number. Radius rises as a square of a principal quantum number. So for the second state, atom is already 4 times bigger. As you remember, in the atom, the principal quantum number can reach a few hundreds. But in the exciton, this value is way lower. How lower? In this case, it's limited by, I would say, 25, 30. But again, you begin with a higher size of 400 times.
So it actually makes it just bigger.
Yeah, I guess you can end up with a size of 1 or 2 microns, or probably
Okay.
3 microns. It's not that big, but you again already have no problems with the atom. If you have one atom, how to hold it?
Okay. So
By-
yeah, like it's
By
being.
laser squeezers. It's not a simple business. But here you have it in solids. For most application, you don't really need this 25th number or 20 or 30s.
How much do you need?
The ground and one exciter probably for the for my work, they are interested in the first and second excited state because they give you entangled photons. But for the most applications, indeed, like the current, you need the ground state.
Okay. Yeah, so that's the main thing, and actually the main advantage in application. Yeah. Or how it can be applied mostly, because.
First of all, I would add that the thing,
Yeah.
we basically were speaking about the topic without naming it.
Yeah, that's true.
You know how it's called? It's a Rydberg atom.
Yeah.
It's Rydberg atom and respectively Rydberg exciton.
Rydberg. Rydberg mountain. It was a stupid joke. Yeah. So yeah, Rydberg atom and.
What is and Rydberg exciton? Rydberg is actually a guy who first found that they are levels. How it was, he just placed some, let's say, material into a flame and found that it's colored. Like, if you burn nickel or whatever, you see different colors. And he looked through the spectrometer or like monochromator and found that the color is defined not by just color, but because of lines.
Yeah, so
And
these lines are the levels that you mean.
Yeah, and the lines corresponding to difference between different levels. And it was begun of the spectroscopy. I don't know if he got Nobel Prize. I guess he lived...
Or maybe people who watch it, they will Google and help us, no?
No. I guess I will just say that it was far before Nobel Prize.
Do you think so? Okay, let's Google it afterwards and see.
Yeah, let's
Actually,
Google.
it's good to put it like, on a timeline, yeah, to see when it happened. Nice.
Yeah, and this...
It made it way easier
Yeah.
for the other scientists and researchers in that case.
Yeah, he basically establishes the area.
Yeah, like we dig here and then this title to make it bigger, no?
Okay.
So yeah, today we spoke about actually how to call it and to put it into words. The biggest problems of man, and
In terms of quantum physics.
yeah, yes, and that is the best way, yeah, to put it and to arrange it. But it was really nice, and with every time I've got to find and discover new and new things. So thank you. And what's gonna be the next topic or the topics? Just to put a teaser,
Tough. Do you know what are the artificial atoms?
No, I just heard just some stuff, but I think you have to make it, like to discuss it and to make it full presentation of it with all the steps.
And we need some feedback if you write we need artificial atoms or just something like that in comments.
In comments. Because that's the best thing also, or maybe people can write what they are interested in, right? Or some questions that they have.
There was surely a Nobel Prize about it.
I love the Nobel Prizes. Okay, good. Oops. Yeah. So, thank you very much.
Do not forget about that Crina has Instagram where she discusses wine tastings.
Yeah, and Alexander has also an Instagram page. He has other channels where he speaks about science. So please follow his
About
channels
academic things. It's
Yes.
basically their tips how to do. Like if you do science, if you're like master, PhD, if you're a bachelor student, you will be interested in this topic. How
Yeah.
to write bachelor thesis, how to write scientific paper.
In pain. In pain and with a lot of stress. Not sleeping the last 2 weeks of it.
No tips how to do, not about time management.
But most of the students, they did it. I mean, it was like that. But yeah, actually, there were students who did it organized, and or maybe students can start it the last 2 semesters if they know the topic. So there you can find all the tricks and a good guideline that Alexander is gonna give you.
And thank you for watching. Do not forget to like us.
Yeah, follow, like, and come to the next video.
And share with friends who will find the video interesting.
Yeah, and you can also leave your impression. All the impressions are welcome. What we can make better.
They do not know physics.
Yeah, for sure. It's about me. But I can drink wine. Okay, good.
Excellent.
If you kept watching up to this moment, I am really thankful. I do remind I am full-time researcher studying physics, and I have Telegram and Instagram where I tell about my life, daily life in science. Crina is an ambassador of wine and culture of Republic of Moldova. Follow her on her Instagrams. Please for support like this video, leave a comment and share with a friend of you who might enjoy this. And see you in the next videos.